Hello, my name is Jennifer Wilcox. I'm a professor of chemical engineering at Worcester Polytechnic Institute. Today I'm going to talk to you about the industrial sector and looking at the waste heat produced on site for industry and how we can look at decreasing this wedge in terms of difficult to avoid emissions. First, I want to unpack the emissions associated with the industrial sector a little bit. Roughly 30% of all US emissions are associated with the industrial sector, so that's just under 2 gigatons of CO2. These can be separated in terms of direct or indirect emissions. Indirect emissions are those associated with, say, electricity production that's not taking place on site at the facility itself. Direct emissions are those that are taking place on site and typically are divided between on-site combustion for heat, but also process emissions. So in the industrial sector, you have things like cement production, steel production, refining, and you have both on-site combustion where you need to supply industrial heat, but you also have process emissions where you have a chemical reaction that produces CO2 from making the product itself. When we look at those emissions in terms of what's on site, what a facility, an industrial facility has control over capturing, it's roughly 1.4 gigatons of CO2. In this work, we are not focusing on petroleum, natural gas recovery, or coal mining. So there's a number of other industrial applications where carbon capture retrofit isn't necessarily a way to reduce that wedge in terms of carbon emissions. And natural gas recovery, we already have commercial technologies to purifying natural gas for pipeline transport today. We have membrane-based separation, we have adsorption-based separation, and the reason why we're not really focusing on that is because those technologies are pretty straightforward today and they're commercially available. When you recover natural gas out of the earth, it's already pressurized, so you have a significant driving force for separating CO2. Oftentimes, too, the CO2 is an elevated concentration, making it further easier to separate. And so what we're really focusing on this work are the sectors that are really difficult to avoid. So cement production, refining, steel production, and these examples. And so roughly half of the emissions associated with these sectors that I'm discussing, the emissions are coming from on-site combustion or stationary combustion, where the other half is really associated with the process emissions or the chemical reaction that produces the material and thereby also produces CO2. So when we look at just those areas, what we have here, I'm showing the cement, and you can see the on-site combustion associated with cement here. And then you have iron and steel production, and then the stationary combustion associated with that. And so in iron and steel production, you have the process emissions, but you have a lot of auxiliary heat associated with the process. Whereas when you're producing cement, the kiln itself, for when you're calcining to produce cement, it's the combustion and the process emissions mixed up into one unit. And so you get elevated concentrations of CO2 from some of these units. With refining, it's a little more complicated. Some refineries have hydrogen, some do not. So we exploited that a little bit here. And you can see too, with refining, you have process emissions, but you also have the stationary combustion. And so it's important when you think of deep decarbonization, you're trying to avoid both the process emissions, which in our work we find is a little bit easier because you tend to have a higher CO2 concentration. And then you also have, in a lot of cases, industrial heat that needs to be decarbonized, which is a little bit more difficult because you have a lot of maybe process heaters or boilers on site and they're not necessarily coupled together. So you have a lot of distributed units and you have to figure out how to decarbonize those heat sources. So you can think about deep decarbonization as kind of decoupling those. And there's only a couple of cases where the two are actually together, which is with the cement kilns and also with the steam methane reforming for hydrogen production. This is just a little bit of some of the numbers. So with the cement and steel industries, this is the number of plants. And then you can see the breakdown again. So for cement production, because you're burning the fuel in the calcining unit where you're producing the cement, the process and the stationary combustion are really all in one. Whereas for iron and steel, you know, if you look at on site and you have a blast furnace, there's a lot of other auxiliary heat units associated with that. So the primary process unit would be the blast furnace, and then you have also stationary combustion that's separate from that unit. So you have kind of two carbon footprints that you have to think about decarbonizing. In terms of refining, it's a little more complicated. You have some refineries without hydrogen and some refineries with hydrogen. The major process unit at a refinery is the catalytic cracker. And so we were looking at, retrofit of carbon capture to the catalytic cracker in this case, to the blast furnace in the case of steel, and then to the cement kilns in the case of the cement manufacturing. These are just some basic process flow diagrams of how the CO2 is created. And if you want to dig into this in more detail, you can see this recent publication that came out of our group, and it was recently published in Environmental Science and Technology. And so we've done also here, you can see the blast furnace in an elevated concentration of CO2, because again, you're producing it by a chemical reaction, CO2, but it's also mixed with combusting fuel. So you have a mixture of the exhaust from fuel combustion combined with the process emissions, which elevates the CO2 concentration ultimately. But then you have a lot of auxiliary heating units that are required. And so with steel production, you have multiple. You have to decarbonize the heat footprint for on-site combustion, but also the process unit. And so similar with a catalytic cracker, this is just one unit. The catalytic cracker is really there as the primary process unit to make all of the chemicals and hydrocarbons of interest. And you have a slightly elevated CO2 stream from this unit. And then you still have, at a refinery, have a lot of other heating units that need to be decarbonized. And so what we did is we separated some of these primary industries and their stationary combustion versus their largest process units. And so when we think of carbon capture retrofit opportunities, we look at these units, the process units. And the reason why that's important is because we notice that the CO2 purities are much higher than they would be from just the exhaust of combusting a fossil fuel. And so because these purities are higher, that means that it's going to be easier to actually do the separation process, because what makes a separation process expensive is by having to handle all of the inert materials and not the CO2, which is the molecule that you're actually interested in separating. And so the more CO2 you have in your stream, the higher purity of CO2 in your stream, the easier in terms of energy the separation process is. And so by focusing on these units, which are the largest emitters on site and with the highest concentrations, we can really look at what's a cost-effective route of taking just a step-by-step, decarbonize the process emissions first, then followed by decarbonizing the heat emissions second. The other piece is well, when is this going to happen? And when you ask that question of phasing out to new technologies, we had to actually look at the age of the process units for each of these sectors. So we looked at cement, iron, and steel, and in this case, refineries with and without hydrogen. So we notice here that in the next 20 years, 48 of this just accounts for about 85 of the cement kilns of the 91 in the US that we could find the ages for. So about 48 are going to be phased out over the next 2 decades. But another 37 won't be phased out until beyond 20 years. And so what that means is in the early days, maybe you just replace these with new units like oxy-combustion, for instance. But these ones that are going to be around a lot longer, and maybe some of these on the tail end, you could retrofit with carbon capture at the exhaust. Same with iron and steel. So we look at, there's a lot of blast furnaces. In the next decade, we see a lot of them reaching a retirement age. But from 2030 to 2040, there's still a fair number that represent a good portion of the carbon footprint associated with this sector that could be retrofitted with carbon capture since they still have some life left. With refineries, as long as we continue to use and depend on crude oil and liquid fuels from crude oil, retrofitting with these, retrofitting the catalytic cracker with carbon capture could also be an opportunity for early stage deep decarbonization. We took data from a couple of different reports here so that we could understand the waste heat potential in the United States. And so because all of these streams that we took from the report, it was a sector by sector, state by state, they were all of temperatures greater than 230 degrees C. So that's a high enough quality of thermal energy to take waste heat to power if we needed to. When we were looking at carbon capture a lot of the energy associated, we're specifically focusing on solid sorbent-based technologies. And so with those, a large portion of the energy pie is associated with thermal regeneration of the solid sorbents themselves. There are portions that require, maybe a little bit of vacuum, compression, fans to overcome pressure drop, or blowers to overcome pressure drop. So there is a little bit of an electric footprint too, electric energy footprint. So some of this waste of power could be useful for the separation technology, but a lot of it is just direct thermal energy. And so we took all of these streams of that quality to see what the potential could be. And this is a breakdown from the sectors. So we have refining, we have primary metals, which isn't just iron and steel, but also aluminum and copper and some other metals. We're also looking at minerals like cement, of course, but lime and glass. And so we look here at the number of facilities, but also the capacity of each. So we did two things. We looked at point source capture potential, so looking again at the largest process unit associated with each of the sites. And then we also, in some cases, there was still an abundance of waste heat available. And so in those cases where there was an abundance, we also looked at the application of direct air capture in order to decarbonize that sector even further. There's a technology today called Savante that actually is looking at these types of applications. They have projects ongoing, for instance, with the cement industry, in looking at carbon capture retrofits to the exhaust of cement kilns. And so this is something that is already taking place today. And then in terms of direct air capture, we were really looking at a Climeworks type of a process where, again, it's solid sorbents. It's roughly a split of 20% electric energy and 80% thermal. And then there are other opportunities where you see these kinds of companies like CarbonCure or Solidia in requiring CO2 for their process, and also having partnerships with the cement industry and construction industries. And so this could serve as a source of CO2 for their processes as well. And so there's a lot of synergies between these companies, I would say. And so what we did is really focusing on point source capture, because again, it's the low-hanging fruit, being more concentrated. And then we looked specifically at 3 scenarios to try and show that out and follow it through. One is looking at point source capture coupled to direct air capture. And when we needed electricity for the process, we looked at this example was associated with obtaining the electricity externally. And so what that means would be from the grid. And what we also did was, given the carbon intensity of the grid at a given location, we took that into account. Since we're thinking about direct air capture, that's going to reduce the net removal of CO2 from the air by taking into account the CO2 intensity of the grid at the location of the facility. We also looked at, forgetting about point source capture, we know that there are incentives to do direct air capture, like the low carbon fuel standard in California, which applies pretty much anywhere. And so it may be economically interesting to actually explore these facilities doing direct air capture. But what we found, because the point sources are so much more concentrated, you get a lot more impact. And so future policies, could be modified such that there would be incentive also to reduce the carbon footprint associated with the point sources associated with the industrial sector. Because you'll see in this work here, when we looked at petroleum refining, for instance, we've looked at 103 different sites, the primary metals 91 sites, and minerals 80 sites. And we looked at the available waste heat associated with each of these sectors. And then the total impact potential when you apply point source capture and direct air capture is about 105 million tons, so 0.1 gigatons across the sectors. And then when we looked at dedicated, scenario 2, where we looked at dedicated direct air capture coupled to offsite electricity, so relying on the grid, you see the impact is much less. So here we get a total of 105. When you look at just direct air capture with offsite electricity generation or from the grid, it's 26.6. And then if you were to do waste heat to power using that high quality waste heat, you are reducing even further because in this case, you're getting the electricity and the thermal on site. Everything's done on site. And so you get about 15 million tons of CO2. So again, because it's just easier to separate energy-wise and ultimately cost-wise from more concentrated sources, you get greater impact when you start with point source capture. And we're showing that graphically down below here. And so you can see petroleum refining, and then the point source captures in yellow, so you can kind of see this greatest impact. We also show that you have the stationary combustion, which we're not touching here. We're really just retrofitting carbon capture to the process emissions that generate, you know, the greatest amount of CO2 on site. And so decarbonizing the industrial heat would be a different piece. And so we wanted to look too, so again, this is the total potential, 105 million tons of CO2, and we did state by state, and we also overlapped this with the sedimentary basin storage because in order to have significant impact, you need to do something with the CO2 that permanently avoids emissions from the atmosphere, or in the case of direct air capture, permanently removes CO2 from the atmosphere. So we have a positive impact on climate. And so we looked at each of the sectors individually, but then when you total them all up, you can see actually some pretty significant impact potential in the state of California, somewhere between 10 and 20 million tons of CO2. So again, associated with the industrial sector. And so here, the state of Texas also. And the nice thing too is that you have this potential coupling to the sedimentary basins to actually permanently remove or avoid that CO2. This is looking at the scenario where we have external electricity, but just dedicated direct air capture. And we have another case, remember, where we take standalone. So in this case, the quality of the heat, again, was so significant, over 200 degrees C, that we were able to take that heat and actually produce power as well. So these would be everything all-inclusive at the industrial facility. And what this means too, ultimately, is that if you're a steel producer or if you are producing cement, you have the potential of not just producing that product like you do today, but by doing this and retrofitting with carbon capture and using waste heat, you're not modifying the material that you're producing at all. And what you are doing, though, is decreasing the carbon footprint associated with that material that you make, which could have a significant impact. And so with that, I'll end. But thank you so much for joining me today. And for your reference, there's a series of references here if you're interested in learning more.